So here we've defined, so the P1n, or PN sometimes for short, is the probability of beta-delayed neutron emission. So P1n is the probability of beta-delayed neutron emission, and the energy available for the neutron is less than or equal to Q beta n, which is the difference between the Q beta and the neutron separation energy. But that's not quite true. You also have to take into account the energy of the recoiling emitter nucleus, which is small, but it does matter. So beta-delayed neutrons are prevalent throughout physics. So for example, they're important for nuclear structure because they're a common decay mode. It can tell us about the structure above the neutron separation energy, especially if there is competition between neutron emission and gamma decay from above the separation energy. In reactor physics, delayed neutrons change the dynamic time response of a reactor, which means that we're able to control reactors with human controls because of the long time scales of delayed neutrons compared to prompt neutron emission. Delayed neutron production also persists after reactor shutdown, which contributes to decay heat. And in nuclear astrophysics, it provides a source of extra neutrons in the late stages of the R process, which do affect the final abundances after the sources of neutrons have already extinguished. For nuclear astrophysics, having beta lifetimes and as well as the probability of 1 neutron emission, 2 neutron emission, etc., is really important to constrain models. So at the bottom, there's a table which is 6 years old now, so the numbers might have changed somewhat, but it lists the numbers of energetically possible cases for 1 neutron emission, 2 neutron emission, etc., and how many of those cases have actually been measured. So the majority is been measured is the 1 neutron emission, but still only a third of the cases have been measured. For 2 neutron emission and higher, it's much harder to detect. So one area to highlight is the R process, which produces very neutron-rich nuclei in high neutron flux environments. So there are 2 types of R process. There's the hot R process, which happens inside core collapse supernovae with high neutron densities of around 10 to the 20 to 10 to the 30 per cubic centimeter. And in this case, neutron capture and photodisintegration are in equilibrium for a considerable amount of time. So for this type of R process, knowing the neutron separation energy is very important. In the cold R process, this happens inside neutron star mergers, the evidence of which came with the observation of the gravitational wave back in 2017. In this case, the neutron capture and photodisintegration equilibrium rapidly breaks down before the neutrons are even used up. So in this case, a nuclei will continue to capture neutrons until the beta decay half-life is too short, and then it will beta decay before it can capture a neutron. So in the end of the R process, called freeze out, the neutron density drops, and then the neutron capture stops because there aren't enough neutrons to capture. So then the material will decay back to stability. However, if the probability of 1 neutron emission or 2 neutron emission is large enough, then the decay path will change. So for example, here, rather than populating this A equals 134, stable mass chain, if indium 134 undergoes 1 neutron emission or 2 neutron emission instead, it will populate mass chains 132 and 133. So knowing detailed information about the beta-delayed neutron emitters will help us give a more complete understanding of our process nuclear synthesis, but also the abundances that have the final abundances inside stars. So it's an important decay process for a lot of physics. So how do we measure it? So in general, there are 2 ways of measuring. You either detect the neutron directly or you try to avoid the neutron altogether. So direct neutron measurements, you can use for example, proton recoil counters and helium-3 counters. These measure the probability of neutron emission really well, which is very important for the R process. And it can infer neutron energy, but it is complicated. If you're using intense beams, it can have problems with beam-induced background, neutron scattering. There's also a lot of work on novel scintillators that is happening right now, and scintillators like CLIC, which do have advantages for measuring neutron energy, but they can be worse off in efficiencies. Neutron time of flight detectors are also very popular. So for example, Vandal, it can measure neutron energy in PN, but there is a trade-off between efficiency and resolution. And again, it can have issues with beam backgrounds. For indirect measurements, measuring beta-delayed gamma emission is the easiest experimentally, because all you have to measure is a beta tag and then the gamma rays. But this requires a lot of assumptions about the spectroscopy. So you need to know the gamma feedings, neutron feedings, if there's electron capture that's present. So this gets complicated very quickly as to whether you can analyze the data and get the true message from the data. Then there's Recoil-ion spectroscopy, which is the focus of this talk. The unique thing here is that we can measure the energy of the neutron and the probability of neutron emission simultaneously. We don't have the difficulties with neutron detection. Sorry, we avoid the difficulties with neutron detection by we don't need to detect the neutron. We don't have the difficulties with background, beam-induced background, because we don't need a lot of beam. However, we can't measure 2 neutron emission or 3 neutron emission without extra detectors. So the principle of Recoil-ion spectroscopy is this. So with beta decay, you have a beta and a antineutrino that are emitted, and the daughter ion recoils. And you might see gamma rays emitted from excited states in the daughter. But with beta-delayed neutron emission, you get the beta and the neutrino, but you also then get a neutron. This occurs with the branching ratio P1N. And this emitter also recoils, as it does with straight beta decay. But if we confine these precursor ions to a trap, we can then access this low energy recoil, which you can't do in any of the other experimental techniques. So we can distinguish the decay modes. So we can distinguish between beta decay and beta-delayed neutron emission by just looking at the time of flight of this recoiling ion. So by detecting only this ion and the beta in coincidence, we can reconstruct information about the emitted neutron. So we can reconstruct the energy and the probability of beta-delayed neutron emission without detecting the neutron. And that is the key to Recoil-ion spectroscopy. So a piece of apparatus that we used to measure this was the beta decay Paul trap, which was located at Argonne National Lab. This was actually originally built for precision beta decay studies, and it was used to measure, this A beta nu term is the angular correlation coefficient between the beta and the neutrino. And it also measured correlations between the beta, the neutrino, and an alpha particle of lithium-8. And then it was adapted later for use for beta-delayed neutron emission. So what you can see here is the trap frame, which is a square frame, and you can see these plates, and they're the plate electrodes. So a cloud of ions, which means it's maybe 1,000 ions, are trapped in the potential at the center of the trap, and they do form a sort of cloud. So we do refer to it as an ion cloud, and it's trapped in between these electrodes. What's missing from this photograph is the detectors, because then you wouldn't see the trap. So this schematic shows this X here again is these electrodes, and we have 3 different types of detectors. We have MCP detectors, which are microchannel plate detectors. These are 90 degrees apart. We have plastic delta EE detectors, which are also 90 degrees apart. And then we also have 2 germanium detectors pushed up against the side of the trap. So you'll note then that the MCP and delta EE pairs are either 90 degrees apart or 180 degrees apart, and that will become relevant later. So to measure Recoil-ion spectroscopy with the beta decay Paul trap, you confine this ion cloud into the center of your trap, and then the precursor will undergo beta decay or beta-delayed neutron emission depending on the branching ratio. For beta decay, we detect the recoil ion and the beta in coincidence, and we measure the time of flight of the recoiling ion. And that here is defined by the start signal is when you detect the beta in the plastic detector, and the stop time is when you get the recoil ion in the MCP. The beta-delayed neutron emission, you're still detecting the recoil ion pairs. So you're still measuring the time of flight of the recoiling ion, so you'll still detect the beta and the recoil. You won't necessarily detect the neutron, but what's different here is that the recoiling ion gets an extra kick of momentum from the neutron, and that's how we're able to distinguish the different events. So the time of flight is used to then infer the neutron energy and the probability. And just to show you some experimental data, so this is ID 137. This shows how well we can separate the beta decay. So this is the time of flight of a recoil after beta decay, and this small peak here, which is very well separated, are the recoils after beta-delayed neutron emission. So it does get a good kick. So for example, for a mass around 100 nucleus, if you have a 1 MeV neutron, it will give the recoiling ion a 10 keV kick compared to a 0.01 keV kick from a beta. So it is significant. So how do we infer the neutron energy then? We can write it in terms of masses and velocity. So we can write it in terms of the mass of the recoiling ion, the neutron, and then the velocity of the recoiling ion. And this works if we assume that the neutron momentum and the recoil momentum are roughly equal and opposite, and we ignore any contributions from the beta and the neutrino and any gamma rays. So the velocity of the recoiling ion we measure because we can measure the distance from the ion cloud at the center of the trap to the location where it hits on the MCP. And then we can also measure the time difference between the beta and the MCP, which gives us the time of flight of the recoiling ion. So this is how we infer the neutron energy. I said earlier that we can also infer the probability of beta-decay neutron emission, which is just defined by the number of nuclei that undergo beta-decay neutron emission divided by the number of nuclei that undergo beta decay. So this number, which is the number of nuclei that undergo beta-decay neutron emission, we can count. So this is just the integral of the peak of the recoil ions with the short time of flight. For the number of betas, we have 3 independent ways of measuring it. We can either look at the counts in the delta E detector, we can look at gamma ray singles that are tagged with a beta, or we can look at beta recoil ion coincidences, I'm sorry. So beta singles are less sensitive to how the beta decay mode that occurs, but it is prone to background. Beta gamma singles are insensitive to other different types of decays, but we must know the gamma ray branching, which in some cases is very difficult to know. And the beta recoil ion method is affected by the RF. So they're not perfect, but we do have 3 independent ways of determining the same number. These signatures are very selective. So we're looking for a very clean signal with very low background, and we can use very weak beams to look at this. So a lower limit is around 0.1 ions per second. So to show you some data to show you that this works, so we're looking here at iodine 137 and 138, and cesium 144 and 145. The blue spectrum is from the BPT, and the grey or the red in the background are from other techniques. So the other techniques include proton recoil, proportional counters, and ionization chambers. And you can see that the BPT recreates the neutron energy spectrum very well. And this is, I think it's incredible given that we don't detect the neutron directly, whereas the other methods they do. You can also notice that we have the PN values that we extracted from these works. So in every case, they agree with an uncertainty as the IAEA published probability. So we definitely have a technique that works. So how does when we're reconstructing our neutron energy, we can introduce a spread in the neutron energy by our experimental measurements. So if we look first at the errors associated with measuring the distance and the time of flight, but how do we actually do this and make a robust study of it? Well, we do it through a simulation. So when we're simulating things, we can isolate each different phenomenon and we can really control the physics. So we create a beta decay input from an event generator, which was originally developed for beta neutrino angular correlations. And then we simulate decays of precursor to imaginary states. So we can set the neutron energies that we want to populate, essentially. So for example, I want to populate neutrons generate energies of 100 keV up until the Q beta n value in 100 keV steps. And I'm able to do that by essentially generating fake states. Then we can compare the inferred neutron energy to what I know the simulated neutron energy should be. So I can compare my 100 keV neutron to the value that I'm inferring to see how well we're actually inferring this neutron energy. The simulations have all been benchmarked by data, meaning that the simulations are, we're simulating the recoils and we're simulating precursors inside the BPT, which is an experimental setup. And so then we can compare all the physical measurements we've made to our simulations to know that our simulations are actually working. For this work, we're assuming that the beta decay is a loud Gamow teller. It does restrict then the spin sequences things can go through, the states it can populate, but it also fixes the value of this beta neutrino angular correlation to be negative a third. So the simulation process then, we generate events and we control the physics completely. So we can set the emitted neutron energy, we can set the correlation coefficient, so for example, between the beta and the neutrino. We can set the ion cloud size to either something that's completely fantasy or something that's actually realistic. We can also choose the type of decay, so we can set the probability of Beta neutron emission. This event generator then feeds into two programs, so the SimIon and Geom4. SimIon computes the electric fields based on the geometry of the electrodes inside the trap, and then it also determines the trajectories of any ions that move within the trap. Whereas Geom4 will calculate energy losses of the betas, the gammas, the neutrons in all the materials in the trap, not just the detectors. It also gives you an idea of the energies that are deposited within the active volumes, so in the active volumes of the detectors, and also it will simulate scattering inside materials. We then combine these two outputs together, and then we actually do some corrections to them because we want to make them match the experimental data, essentially. So we can apply detector thresholds to the plastic detectors and the MCPs. We can apply efficiencies, which is what we see in experiment. And we also use the same fiducial cuts that we use on the MCP for the data. So the precursors we're going to use in this study, I've chosen three. So it's iodine-137, antimony-135, and yttrium-99. Iodine-137 is an IAEA benchmark for beta neutron emission. It's in the heavy mass peak of fission. It's very well studied with a variety of techniques, so we'll know if we're going wrong with this one. And the Q beta N value is 2.02 MeV. We chose antimony-135 because it has a much higher Q beta value, but it is also important for the R process. And yttrium-99 is a precursor from the light mass peak. It's relevant for nuclear energy studies, and its Q beta is in between the two at 2.5 MeV. So what affects our neutron resolution? So we measure three things essentially. We measure the distance between the center of the trap and the MCP, the location it was hit. We measure the time of flight, but also we measure the counts incident on each detector. There are errors in our measurement of time of flight. So there's a 3 nanosecond timing resolution, which for a typical time of flight of 300 nanoseconds is around a 1% effect. We also approximate that the trajectory of the Recoil-ion is a straight line, although this will be slightly curved due to the electric fields, but this is a very small effect. And then there's also errors in the distance measurement. So there's a position resolution on the MCP of 1 millimeter, and at the most extreme case of detecting an ion in the corner, it gives an error of less than 1%. So these are all really small effects. But the big effect is the ion cloud. So we don't know where the decay happened within the ion cloud. We're assuming that the ion cloud itself is a Gaussian distribution in 3 dimensions, and it was experimentally determined to be around 1 millimeter cubed for antimony-134. But how do we determine the actual effect of this ion cloud size on our reconstructed neutron energy, which is E prime? We simulate. So we can simulate both a realistic ion cloud of 1 millimeter cubed, and then a point-like ion cloud just to switch off the effect. And that's what we did. So this is simulated data now of iodine-137. So I've separated the data. We have the 2 angles. So in red at the top, we have 90-degree data. So this is where you have the MCP and the plastic delta E detectors at 90 degrees apart. And then the bottom in the blue are it's the combination of the MCP and the delta E 180 degrees apart. The left-hand side, these 2 histograms here are where we have a point-like ion cloud size. And then on the right-hand side, we have a 1 millimeter ion cloud size. The numbers above some of the peaks are full width half maximum in keV, just to give you an idea of how much it actually deteriorates. So you can see for the point-like ion cloud, if we're looking at resolution, it looks like it gets slightly worse, but then it gets much better towards high neutron energies. But there's a marked difference in the 1 millimeter ion cloud, which really does disintegrate with increasing neutron energy. If we look at how the neutron energies themselves are reconstructed, the dotted lines here show the neutron energies that I simulated. So you can see for the 90-degree data, the centroids of the peak match very well with the dotted lines. But at 180 degrees, in every single case, is an overestimation of neutron energy. Why is this the case at 180 degrees? Well, earlier I said that we made the assumption that that we can ignore the beta and the neutrino and the gamma rays, but actually it turns out we can't. So these are precision measurements, and if you want to make precision measurements that are good, you can't ignore any kind of effects like this. So there's actually a triple correlation between betas, neutrinos, and neutrons that affects the reconstruction of our neutron energy. So how do we look at this? So if I take two extreme examples. So I take the one example on the left-hand side where the beta and the neutron are emitted basically parallel. So there's no angle between them. In this case, if you think about vector addition, this beta gives the recoil an extra boost. So the recoiling ion is roughly equal and opposite to the neutron, but with this beta momentum in the same direction, it's giving extra boost to the momentum of the recoil. An increased momentum is a lower time of flight, which is an overestimation then of our neutron energy. The other extreme is where the beta is emitted perpendicular to the neutron, and here the beta is going to have no effect at all on the recoiling ion momentum. And so in this case, the reconstructed neutron energy is basically the same as the true neutron energy, which is what we saw in the previous plot. So how do we account for this, and how does it really physically affect the neutron energy? So we look at the beta, the neutron, neutrino triple correlations. So W theta here is the phase space, and then we have three different terms. The second term is the beta neutrino term. So here we have the angle between the beta and the neutrino. We have the momentum and the energy of the beta, and out front we have this term we've met before, which is the beta neutrino angular correlation, which is between -1 and +1. For this work, we're assuming allowed gamma decay, so it's set to -1/3. In the triple correlation term, if you look inside the square brackets, we have some angles. So again, it's the angles between all three particles, so neutron and beta, neutron, neutrino, and then the beta neutrino. Out front, we have the momentum of the beta and the energy of the beta, and we have this G12 term. This G12 is on the order of unity, so that means then that these triple correlations have an effect. So let's look at the G12 term, and it can be written as the small g12 times by 1/10 of this tau function. So G12 depends on the matrix elements of the Beta-decay, so the Fermi and Gamma-Teller matrix elements. And this tau function depends on the spin sequence that we go through. So when we Beta-decay from precursor to emitter, and then we emit the neutron to the beta neutrino daughter, the states that is populated affects this function. And what also affects it is L, which is the angular momentum of the neutron with respect to the daughter nucleus. And what that physically means then is that we have a positive G12 value. It means that there's a tendency for the beta and the neutron to be aligned. And a negative G12 value means that there's a tendency for these to be perpendicular. So we expect then our neutron energy to be overestimated when G12 is greater than 0, and it will be about right when G12 is less than 0. What does that mean for us? So we're looking at 3 different precursors, and here are, again, for an allowed gamma-Teller decay, these are the spins that are possible. So we go from the precursor to the emitter to the daughter. But the problem is that we don't know the exact branchings of the spin sequences. So we know that in the emitter, for a 7½ plus ground state is going to be 9½ plus 7½ plus or 5½ plus because it's gamma-Teller. But we don't know, I can't say that the branch from the 7½ plus to the 5½ plus is 90%. So we then have a range of corrections that we have to apply. So an example then of iodine-137, so there are 3 options for the state in xenon-137 that could be populated, and then the ground state will be populated in xenon-136. So as this tau function depends on the spin sequences and L, in this case it's going to be 3 different values of G12. So that then means that we have to simulate all of these possibilities, and we also simulate G12 equals 0, which means there's no beta neutrino neutron correlation. So to reference what simulations we actually have to do, in terms of the number of events, it's the number of decays you want to study from the precursor, which then the neutrons you get is relative to the probability. And then the number of the number of neutron states we actually want to populate, and then the number of G12 values that we're actually going to simulate, and maybe one or more ion cloud sizes. So it's a lot of simulations that we do. So how does this triple correlation affect our reconstructed neutron energy? This is how. So this is simulated data. On the y-axis, we have a ratio of the reconstructed neutron energy to the true neutron energy. So a value here of 1 means that we are reconstructing our neutron energy correctly. I've split the data up into the 4 G12 values that are relevant for iodine-137. And I've also split it up in terms of angles. If you remember, these things affect 180 degrees data a lot more than the data at 90 degrees. So you can see here that there's a big spread in the ratio at 180 degrees. So to pull a number off the graph here, for an 100 keV neutron, if the recoil-ion and the beta is detected at 180 degrees, with the highest value of G12, this nucleus, which is 0.66, our reconstructed neutron energy is 113 keV compared to 100 keV. So it's quite a big spread. You'll also notice that the ordering of the lines here goes from the greatest G12 down to the lowest G12. And again, this confirms what we know about G12 here, given that if it's much bigger than 0, it has a tendency for these things to be parallel and to really boost the energy, to affect the reconstruction of the energy. It doesn't boost anything at all. A more complex example is antimony-135. So in this case, there are 9 permutations of the spin sequences. So there are 3 states that we can populate in the emitter, and then 3 different states we can populate in tellurium-134. So in the cases where there's more than one value of L that could be emitted with the neutron, we assume that the nucleus will preferentially emit the neutron with the lowest allowable value of L. We only simulate that version. There are 2 cases in which the angular momentum of the daughter, which is 134 tellurium, and the coupling of the intrinsic neutron spin has 2 values for the same L. So given that the neutron spin can either align or not align with L, gives us 2 different combinations, which gives us extra values of G12. So actually for antimony-135, we have 11 different values of G12, which we simulate. So how does the triple correlation effect in antimony? It's the same kind of thing as in iodine. I've not plotted all of the G12 values to save your eyes, but here I have the bounds of the shaded region is the high G12 value and the lowest possible G12 value, and everything else lies in between. So again, at 180 degrees, there's this huge overestimation of the neutron energy. And to pull off the point again, this 100 keV neutron is being reconstructed to have an energy of 136 keV. At higher neutron energies, even at 180 degrees, we start to reconstruct our neutron energies very well. And again, at 90 degrees, it doesn't have such a big effect. You'll notice that this scale is much bigger than it was for iodine-137, and that's just a difference of the Q value, because the Q value for the Q beta N value for antimony-135 is just over twice the size of it for iodine-137. And to summarize this, to include the yttrium data, which given the Q value, you'd expect it does lie in between the iodine and the antimony. So the point that I'm really trying to make here is that we're actually sensitive to these effects. So we are sensitive to the spin sequence from the precursor to the emitter and to the daughter. And this is something that we have to take into account when we're looking at Betelgeuse neutron emission. Also to point out, I simulated this with the point size ion cloud because the ion cloud adds an extra dimension of complexity. To bring up this plot again, if you remember, so this is without any triple correlation at all, you remember how the resolution decreases with increasing neutron energy. So now if we take that into account, So this then is the effect of the triple correlation and the ion cloud size. So for each precursor here, there's the data forks. So the upper fork is where is the 1 millimeter ion cloud, and then the lower is the point size ion cloud. So in each case, for each of these precursors, you'll see that the full width half maximum of our reconstructed neutron energy peak increases as neutron energy increases, but for the larger ion cloud, it doesn't really go back to good resolution, which is exactly what you see in this plot too. It really, the full width half maximum here is essentially double what it was at 200 keV, and that's exactly what we're seeing here. Again, I've separated the data into 90 degrees and 180 degrees. And you'll see in terms of resolution, the 90 degree data is slightly better than 180 degree data, but it still has an effect. There's also an effect of a background with the BPT. So the delta E detector can't distinguish between betas and neutrons. And the neutrons do rarely trigger the delta E, maybe 0.2% of the time. But if you have a neutron instant on the delta E, whether you detect it or not, it's likely that in the MCP opposite, you're going to detect a recoiling ion anyway. Whereas if you have a beta that's instant on the delta E, you only actually detect the recoiling ion on the MCP 5% of the time. So having this extra trigger on the MCP when a neutron, after like a neutron ion coincidence at 180 degrees, it introduces a 10 to 15% background effect. But this is only seen in detector pairs at 180 degrees because the neutron and the recoiling ion are emitted back to back. So in reality then, this was simulated and then the effect was subtracted off the data like an efficiency essentially. So in conclusion, the Recoil-ion spectroscopy is a very powerful method for measuring beta decay and Beta neutron emission, and we can reconstruct the energy and the probability of Beta neutron emission without needing to directly detect the neutron. But can we do better? Yes, we can. So the BPT it was originally made for beta decay, and then it was adapted for Beta neutron emission. So what we want to do is build a dedicated setup to only look at beta neutron emission. So the biggest source of broadening in our neutron energy reconstruction was this large ion cloud size. And we're going to reduce the ion cloud size by using a preparation trap before the measurement trap, which will capture and condense and cool and bunch the ion cloud before very gently nudging it into the trap. Reducing this ion cloud, as you saw from the simulated data, will have a big effect on our measurements. The BPT also suffered when ions were sticking to the electrodes and then they weren't decaying from trap center, which then is a background. So we're using rod electrodes rather than those big plates, which have a smaller surface area. And also, if we're using this preparation trap, we'll have increased capture efficiency, which means that we're not going to have ions sticking to the electrodes as much. We want to quantify these backgrounds that BPT was sensitive to, and to get around that, we're using segmented delta E detectors instead. And a new setup that we've designed is going to have a 3 times higher beta recoil ion detection efficiency, which is huge. And with increased solid angles, new delta E detectors with better light guides to allow more light. And then in the future, we'll eventually switch to a digital data acquisition. So this is the new setup. It's called Bear Trap, which is the beta recoil ion trap. So it's around 15 inches across, and it's a very similar design to the BPT, except now you can barely see the electrode. So this is looking end on as the ions are going into the screen. We have 2 Z-stack MCPs, which are more than twice as big. So the solid angle for the MCP is increased from 12% to 20%. We have plastic delta EE detectors again, and the solid angle is also increased with segmented delta E's. And we can then also, we've improved the design so we can lower the threshold. So it'll have a 30 keV beta threshold compared to the 70 keV we were using before with the BPT. And this has been fully funded by Argonne National Lab, Lawrence Livermore National Lab, and Louisiana State University. So here's another view of the inventor diagram. This is drawn by Graham Morgan, who's a grad student at Louisiana State. This is a side-on view, so the ions from the preparation trap will enter this way, and I've drawn a horrible cartoon on top of the particles and the gammas that you expect. So, so yeah, this is a very exciting setup. But I'm going to concentrate on this one thing, which is quantifying these neutron-induced backgrounds. So if a neutron is incident on the delta E detector, it's highly likely that opposite you're going to detect a recoiling ion in the MCP, which leads to the background contribution. Because neutron recoil ion coincidences are detected at 180 degrees, we can use this to identify these events and then remove them from the background. The way I did that was by using simulations again. So with simulations, you have the absolute luxury of knowing what kind of particle hit your detector. So what I did was, if I select that I'm only looking at, say, betas on one segment of our delta E, maybe I should not go on the red one, one section of the delta E, I can look at the MCP to see where the recoiling ion was detected. So if I gate on a beta hitting a delta E, and then I plot a histogram of all the recoiling ions that are in coincidence with any betas that hit this one segment, what do we see? So this is the histogram, and these represent the physical area of the MCP. Now they're numbered 1 to 4, and that corresponds to the delta E segments of the plastic. So these are also labeled 1, 2, 3, 4. So in this case, histogram labeled 1, this is all the recoiling ions in coincidence with a beta that was detected in this one quadrant. And you'll see that this is homogeneous. This is very smooth, which means a recoiling ion is equally likely to be detected anywhere on the opposite MCP. Instead, if we now require that a neutron has hit the delta E detector and we do the same thing, you'll see something incredibly different. So again, this spectrum label 1, this histogram label 1, corresponds to any recoiling ions in coincidence with a neutron hitting this bottom right segment of the delta E. And you see the majority of the recoiling ions in the top left, which is 180 degrees away. And so 96% of the time, we're detecting these neutron recoil ion pairs completely back to back. So even in the experiment where we can't distinguish between a beta and a neutron, this gives us a very good idea of what actually that a neutron might have actually hit the delta E, and then we can analyze these data in a different way. So the current status. We're currently building bear traps. So the MCPs have been manufactured and tested by Quantar, and here is a photo of one of them. The Delta EE design has been finalized and the order's been placed with Elgin, and hopefully you'll be with us fairly soon. The preparation trap design has been finalized, and we're currently designing and building the beamline components, because bear trap is going to be installed in Area 1 at Argonne National Lab, which is the low background area where the tandem used to be. We have 3 approved experiments already with Caribou. So the commissioning experiment is going to be our old friend iodine-137 with the beta neutron emission, and rubidium-92, which is undergoes beta-decay, and that's to study the 0 plus to 0 minus first forbidden transition. We have an R-process nucleosynthesis experiment, which is tin-134 to 136. And then also looking at 6 different isotopes of yttrium for nuclear reactor studies. In terms of the future, for bear trap at Caribou, there's a whole range of isotopes that we can study. So taking the lower limit of the beam that we need is 0.1 particles per second, this blue envelope represents all the beams available at Caribou that have an intensity greater than 0.1 particles per second. The grey path here represents an R-process path. So this is from cold R-process from kilinovae. And these coloured boxes represent isotopes that were singled out in a study from Mumpower and Sermon that have maximum sensitivity for R-process studies. So you can see there's a whole bunch of isotopes in this envelope that are going to have a big impact on R-process studies that are available at Caribou. When New Caribou comes online, so New Caribou, if you don't know, so Caribou is a Californian fission source. New Caribou is going to be a neutron-induced fission source using uranium-235. So the yields are going to be slightly different from Caribou itself. So for example, Indium-132, which is around here somewhere, has a 10 times higher yield from uranium-235 fission compared to Californium-252. One very good advantage about running at Argonne is that there's the MR-TOF, which will then produce an isotopically pure beam at the expense of intensity, but intensity is not something we're so worried about. But again, you can see, looking at the sensitivity study, there are a lot of isotopes that are ready to study at New Caribou. Looking slightly further into the future, the N=126 ion beam factory is going to come online, which is going to be very key to look at the third R process peak around A=190. But this is completely unknown territory, so masses need to be measured, half-lives need to be measured. Without that, we don't know Q beta, we don't know neutron separation energies, we don't know where beta neutron emission is actually happening. So until when this goes online, we've measured the masses and the half-lives, then we'll be ready to do spectroscopy to look at the isotopes around this A=190 third R process peak. Potentially, while we're waiting for the masses and the half-lives to be measured, we could move bear trap to FRIB. So this is similar to the previous figures. The black envelope represents the full FRIB stop beam intensities, anything that's greater than 0.1 particles per second. And again, I've overlaid the R process path and the isotopes of maximum sensitivity from the Mumpauer and Sermon study. So again, here, there's a lot of isotopes that we can study. The key thing, and I think it's worthwhile to point out again, is that we do not need a lot of beam. So whereas some setups need a good chunk of beam, and being from a transfer background, I'm always very wary about beam intensities, we do not need a lot of beam. So there are plenty of isotopes that we can study that other setups might not be able to. So in terms of the future, there's already a lot to study at Caribou after bear trap is commissioned and we've done our first few approved experiments. New Caribou is going to offer a different fission distribution. So that's going to be key to look at isotopes that are relevant for nuclear reactor studies and that kind of thing. I would like to expand to beta-2 neutron emission, which is also key, but the only way you can do that is by adding extra neutron detectors, which means potentially collaborating with other people, especially at somewhere like FRIB, and collaborating with people with big germanium arrays would be really good too, because right now we use 2 clovers, which isn't very efficient. But if we collaborate with these kind of people with these instruments, there's opportunity to have precision beta measurements, beta gamma, beta neutron, and beta neutron gamma measurements. When the N=126 ion beam factory comes online, there's a lot of work to expand knowledge around A=190. But it's also it'd be really fruitful to work in collaboration with other people measuring Beta-decay, for example, like the MTAS group. It really helps us if we know the spectroscopy first. So in conclusion, the real conclusion this time, so Recoil-ion spectroscopy, I hope I've convinced you, is a powerful method for measuring precision beta-decay and beta neutron emission. It's especially powerful because we can measure the neutron energy with good resolution and good efficiency, and also probability of 1 neutron emission without direct neutron detection. The future plans with bear trap is going to be dedicated setup, which to begin with is always going to be an advantage over the BPT, which was never a dedicated setup for beta neutron emission. It's going to be based at Area 1 for a good number of years. So we have the opportunity to make a lot of different measurements, and it has big improvements over the BPT. Bear trap has been fully funded. We're currently building it now. And when we've taken some measurements of Caribou and while waiting for New Caribou to come online, we have a lot of things to measure. And again, to emphasize, I think bear trap in concert with different arrays, so for example, germanium arrays or neutron detectors will be a very powerful collaboration. With that, I'd like to acknowledge all of my fantastic collaborators and thank you for your attention.
Well, thank you so much, Gemma, for a very nice presentation, very clear. And I wish you good luck on the upcoming runs and the future program.
Thank you.
If there is any questions, please raise your hand, and Gemma will answer. Maybe I can ask you a question to start. I may have missed that, but you gave the simulations when you have different types of decays, and you said that you are sensitive, of course, and I think I understood. But the question that I have, if you don't know the decay, or you have some doubt, how unique is the simulation in assigning the decay information? Or
so we wouldn't be using the simulation to assign the spin sequences per se. We're using the simulation to have an idea of how we have to correct the neutron energy reconstruction to then reconstruct the true neutron energy. So we, in some respects, it's not that we don't care about the spin sequence, but this triple correlation is sensitive to the states that it decays through. So it's more to show that this is an effect that we have to take into account. How we take it into account, though, when we don't know the precise branching ratios, it's going to be an average effect. So for these limited examples, because we're limited here to allowed gamma-tele decays, it's still, it's still a spread. It's still an effect. It is a small effect, but we wouldn't use this, for example, to determine what spin sequence we're actually decaying through. If you'd want to do that, you couple it to a germanium detector, germanium array, and do it that way.
I don't know. Yes.
Do I see a hand raised?
Andrew.
Thanks. Hey, Gemma, that was a really nice talk. I learned a lot about precision measurements of beta decay. Could you talk a little bit more about the sources of uncertainty in these measurements and how you beat them down experimentally?
In terms of beta neutron emission or beta decay?
In terms of beta delayed neutron emission. Sorry, that wasn't clear.
And uncertainties in what exactly? So in the probability of neutron emission, or in terms of...
Yeah, so I'm specifically interested in like how you are going to constrain the things that are going into Matt Mumpower and other people's R process calculations, right? And understand there that what they're trying to measure, or what the big uncertainty is, or the big thing in constraining those models is the probability of
Right. So in terms of, maybe I should actually look at, put up the data that we've measured with the BPT before, because that probably gives us a better idea. So this gives you an idea of the uncertainty on the probability of beta neutron emission that we've measured previously. So for the R process, having these probabilities is absolutely key, and that's what they want to feed into their calculations. The uncertainties are mostly going to be from, well, the big one is really the ion cloud size, because you don't know then that distance of where the decay actually happened. And then it's making sure you can really characterize your backgrounds. So for example, if your beam isn't pure and you've got some contamination, especially if they're long-lived, that's going to be a source of background. Having the neutrons that are incident on the delta E detectors and then detecting the Recoil-ion is a source of background. So the key with these precision measurements is knowing the backgrounds and then taking them into account. But I wasn't a part of this experimental campaign, but you can see that we are reproducing the probabilities well compared to the accepted values. So it is a good technique for it. But in terms of how we further constrain it, it's just about building a better array. So having the BPT that's run before, there are things that the collaboration have learned from that, and then how to improve it going forward. So that was what really informed the design of Bear Trap. So my job when I started this position was to do simulations of the BPT and then iterate. So do different detector setups, so there was like a geometry that was floating around where we used 8 different combinations of the delta E and MCP, but it was just too complicated. So how do we, knowing what we know from the BPT, how do we make this better? And just by making the solid angles better, the detection efficiency better, which is going to help, being able to run for more time because statistics is always king. I think that's the only way that would really constrain it, if that answers your question.
It does, very completely. Thank you.
Very good. So we have a question from Kelly, please.
Hey, thank you, Augusto. So we're just kind of following along what Andrew was saying with the ion cloud kind of being the determining factor. Would you actually benefit by having fewer atoms in the trap at once?
I don't think so.
This isn't my, I don't have a good feel for whether fewer atoms actually makes the ion cloud smaller. Maybe it doesn't.
And to be entirely honest, neither do I, given that I've never done an experiment with this kind of setup before. I don't believe so. So I believe that the number of ions in the cloud was chosen, just you have as many in there without them falling out of the trap essentially. Mm-hmm. But what's really going to confine it is how cold it is, how well it's contained. So having the preparation trap that cools the ion cloud, that's what I think is going to be the major effect on the cloud size, rather than the number of, because also there's going to be a payoff, right? If you put like only a few in, which is what you do for like precision Beta-decay measurements, then you're going to have lower statistics too. So I think there's a payoff. Yeah. I think the big one is cooling it, and then by having this cloud pre-trapped and then just gently nudged in to bear trap, I think will be a really big help.
Mm-hmm. Very good. Well, I think we have another question coming up from Charlie Rasco.
Hey, Gemma.
Hey, Charlie.
Nice talk. How much of an impact is the threshold for your neutrons on the PN value?
I'm not sure, actually. Yeah, I'm not sure. So the beta thresholds were important for sure. So having lower thresholds is really going to help, but I'm not sure of the direct impact it will have on the PN value.
So I was thinking more of the neutron threshold than the beta. So like the one like on this picture right here that's up on the screen.
I'm not sure what you mean.
So yeah, basically this grayed out area. How do you account for that?
I don't know. I'll be completely honest.
Oh, okay. Sorry. I just.
No, it's fine. Yeah, having not looked at the data analysis of this, I am not sure. Okay. There is going to be a lower limit to what you can reconstruct, and that surely will be dependent on the beta thresholds too.
Oh yes.
Yeah, because it's all depending on whether you detect the beta ion coincidences, right?
Right.
But I'm not sure what sets that lower limit.
Right, because at some point there could be a whole huge feeding at 2 keV, and you're never going to see that. So
I will find out, and I will email you.
Oh, cool. Yeah, no, that's cool. I was just curious whether you guys had worked through that or not.
I'm sure if somebody's on the line that was on the experiment, they would be able to answer in a GIF.
There we go. Kevin just said something.
Oh.
But still, there's thresholds in all these experiments except for
mm-hmm.
except for the H3N maybe, or the helium. Sorry.
Yeah.
Okay. Well, thanks, Gemma. Again, nice talk.
Thank you.
I want to check with Philip Atsley. Is that a raise hand or a nice virtual clap?
It's a clap. Don't.
Very good. Very good. So I don't see at the moment anymore. So one more question. You talked a lot about this cloud size. I was wondering, because I really no expert here, in the VPT or this trap, can you adjust somehow the cloud size to, I mean, even if you don't know the size absolute, whether relative size will allow you to really benchmark the simulation?
So the ion cloud size, so I did say on one of my slides that the ion cloud size was determined experimentally, and in my backup slides, I put a plot from Kevin Siegel's paper. So the way to determine the ion cloud size is going through simulation, see which simulated value best matched the data. So it was the rising edge of the, so in this case it's for antimony-134 precursor, so it's the rising edge of its time of flight compared to 3 simulated cloud sizes. So when you're doing the experiment, it is what it is, and it's offline that you determine the cloud size. So all you can do in the experiment is just do the best you can in terms of cooling and bunching. And maybe it could be that the commissioning, maybe that's one of the first things we check. So if we're studying iodine-137 again, we have data, we have lots of simulations from iodine-137. That's probably one of the first things that we'll check to see how efficiently we are managing to cool and bunch that ion cloud.
Thank you. Any more questions or comments for Gemma? I don't see any. Maybe you can check, Gemma, too, on your, but I don't see anyone at the moment. So in that case, let me thank you again for a wonderful presentation, and all the best to you. And I would suggest a large virtual applause to close the session. Thank you. See you all hopefully on the 2nd. Okay, well, see you next time, folks. Good luck, Gemma.
Thank you.
See you, Gemma.
Bye.